So we're going to make the jump from making electron configurations to making orbital diagrams. Now, orbital diagrams and electron configurations are basically the same thing, but an orbital diagram is just a tad bit more detailed. It gives us more information about how the electrons are filling into the orbitals that they have available, whether or not there are unfilled electrons or unfilled orbitals, what electrons are paired up, are they individually placed into the orbitals, and so on and so forth. Now, that filling actually determines a lot about the atomic behavior of the atom itself. So while we're doing this, we're going to follow three rules. Firstly, the Aufbau rule, which dictates the order that the electrons fill in. So 1s before 2s, 2s before 2p. As long as you're filling the electrons in the order as prescribed on our periodic table cheat sheet, you're following Aufbau automatically. So it's not really one that you have to worry about. The Pauli exclusion principle states that when you fill electrons into an orbital, they have to be spinning in opposite direction, and we usually limit those directions to up and down. Now, there's a very long explanation behind this that we didn't necessarily go into in first-year chemistry, but for right now, what you need to know is that electrons are in fact spinning around a nucleus of an atom, and when they do that, they're considered to be a moving electrical charge. Moving electrical charges, according to the laws of physics, will generate a magnetic field. So in order for two electrons to exist in the same orbital, they need to have opposite magnetic fields so that they can weakly attract and thus exist in the same space at the same time. Otherwise, those two same charges being so close to each other would repel each other and the atom would just fly apart. So we say if they're spinning both up and down, they'll generate a weak opposite magnetic field. They'll weakly attract and be able to exist in the same place at the same time. The third and final rule that is going to help us during an orbital diagram is called Hund's rule. Now, Hund's rule basically says that as electrons are filling into open orbitals, that they'll fill in one at a time, spacing themselves as much as possible, and only when they need to double up will they double up inside of an orbital system. So let's look at an example of what an orbital diagram actually even looks like. And we worked through the example of sulfur earlier, coming up with an electron configuration. And this would be the electron configuration for sulfur. 1s2, 2s2, 2p6, 3s2, 3p4. A pretty decent amount of information there. Not a whole bunch about how many open orbitals and all of that good stuff. So let's transform this now into an orbital diagram. And this is what an orbital diagram looks like. You can see there's a little bit more information there. So what's the deal with all of these horizontal lines? The horizontal lines that you're seeing indicate how many orbitals are in that subsystem. Now, before we learned about the different shapes of these orbitals. So the S shape was a spherical shape. The P shape looked like two balloons that had the nubs tied together. And the P system had three such shapes. The S system only had one shape. The D system had 5 different shapes associated with it. The F shape would have 7. So these horizontal lines are a way of representing those pictures, just in a more simplistic form. So this is why you're only seeing one line for an S system, 3 lines for a P system, indicating the 3 different pictures that we could draw for it. A D system would have 5 lines, and an F system would have 7. The electrons in this image are pictured as arrows, and notice that on a line, one is pictured going up, one is pictured going down, and that fulfills the Pauli exclusion principle, stating that for these two electrons to exist in the same orbital, they are spinning in opposite directions. And then finally, take a look all the way over at the 3p area. Now notice how the 3p4 was handled. So the electrons filled in one per line. It didn't matter if it was up or down as long as it was on one line, until you had to go back and double up with that last 4th electron. And we just arbitrarily picked that first line to double up on. It's traditional to kind of pick that first line. But if you picked the middle or the last one, it would still be correct. But notice the Pauli exclusion principle was fulfilled by having one up and one down. So let's give another one a try here. How about vanadium? So when we take a look at the electron configuration for vanadium, I get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. So here's how we're going to build this lovely little orbital diagram. I'm going to take that 1s first. S shape. There's only one shape that represents S, so he's only going to get one horizontal line. I'm going to label it as 1s underneath. There are 2 electrons in that cloud. That means it's going to get 2 arrows, one spinning up and one spinning down. So let's start that orbital diagram out. The 2s2 is going to be pictured much the same way. S only has one shape. That means one horizontal line. Label it 2s. 2 electrons go inside of it, one up, one down. 2p6. So the P system has 3 shapes. That means 3 horizontal lines, or places, or orbitals, where these electrons can fill. You're going to label all of those lines as 2p. 6 electrons go inside, 2 electrons per line, one up and one down per line. 3s2, 1 horizontal line, 2 electrons, one up, one down. 3p6, it's going to be a repeat of 2p, just labeled as 3p. 4s2, we've seen this again. So here's your 4s2. Now let's take a look at how we handle this 3d3. So the D shape has 5 shapes associated with it. That means that we're going to be picturing 5 horizontal lines and labeled all of them 3D. But now we need to start filling in the electrons. So again, that's going to be 1 per line until we need to double up. So here's 1, 2, 3. So now notice I still have those 2 empty lines pictured. That's extremely important when you're doing an orbital diagram. You need to see that there's 2 completely open orbitals that could potentially accept some electrons. It's also very, very important to notice that we have the 3 unpaired electrons on the inside of this orbital diagram. And because of that, very unique atomic behavior does in fact occur. We're going to start to talk about concepts like diamagnetism, paramagnetism, magnetism in and of itself, and how these atoms can start to behave with each other. So I hope this little tutorial was helpful to you in understanding orbital diagramming.